Welcome to AWS Mastery Labs, turning AWS chaos into clarity with bite-sized tutorials, hands-on labs, and exam-smashing tips. Data engineering is the discipline responsible for building the foundational systems that enable organizations to collect, store, process, and serve data at scale. It acts as the backbone of any data-driven organization. At its core, data engineering ensures that high-quality, reliable, and timely data is available for analysis, reporting, and machine learning. It's the critical infrastructure that enables everyone from analysts to executives to make data-informed decisions. What sets data engineering apart is the focus on building scalable, maintainable, and secure systems. It's not just about writing ETL scripts. It's about architecting end-to-end pipelines that transform raw, messy data into structured, usable formats that can drive real business value. In part one of this video, we'll explore the key components of modern data architectures, including different types of data, important attributes like volume, velocity, and variety, and how they impact data systems. We'll also cover the data lifecycle, from ingestion to analytics, and examine core big data architectures such as data warehouses and data lakes. Let's get started. Data is the foundation of all digital systems, representing raw facts, figures, or symbols that can be processed to generate meaningful insights. It exists in various forms, including structured, semi-structured, and unstructured data. Structured data follows a well-defined format, such as tables in a relational database, whereas semi-structured data, like JSON or XML, has some organization but lacks a rigid schema. Unstructured data, including images, videos, and free text, does not follow a predefined structure, but holds significant value in fields like AI and analytics. Data is generated from a variety of sources, including user interactions, IoT devices, business transactions, system logs, and external APIs. It can be classified as quantitative, numerical, such as sales figures, or qualitative, descriptive, such as customer feedback. Regardless of type, data follows a lifecycle that includes creation, storage, processing, analysis, and archival or deletion. The importance of data lies in its ability to drive decision-making, automation, artificial intelligence, and business intelligence. Organizations rely on data to optimize operations, improve customer experiences, and gain competitive advantages. However, managing data effectively presents challenges, including scalability, security, integrity, governance, and regulatory compliance. Databases play a critical role in storing and managing data efficiently. Whether through traditional relational databases or modern cloud-based solutions, databases enable structured storage, fast retrieval, and efficient querying, ensuring data remains accessible and reliable for business and analytical applications. Modern data is far more than just large volumes. It is complex, dynamic, and spans across multiple dimensions, making it both challenging and essential to manage effectively. In today's world, data flows in from diverse sources, such as IoT devices, social media platforms, business applications, and cloud environments, each contributing unique data types, speeds, and patterns. This creates an intricate landscape that data systems must be designed to handle. When architecting data systems, it's crucial to recognize the fundamental challenges posed by data properties, as they directly influence the architecture, performance, and reliability of any solution. The traditional three-verse, volume, velocity, and variety, form the cornerstone of these challenges. Volume represents the sheer amount of data that needs to be stored, processed, and analyzed. Velocity captures the speed at which data is generated, processed, and consumed. Variety encompasses the diverse forms of data, structured, semi-structured, and unstructured. Beyond the three V's, additional properties add layers of complexity that are crucial in modern data system design. Value refers to the relevance and quality of the data. Not all data is created equal, and it's vital to prioritize high-value data to drive meaningful insights while filtering out irrelevant information. Variability involves the unpredictability of data. Data sources can change in frequency, format, or quality over time, making it essential for systems to be adaptable and resilient to such shifts. Veracity speaks to the trustworthiness and accuracy of data. With growing concerns over data integrity, ensuring that data is both correct and reliable is paramount to making informed decisions. Lineage involves understanding the origin and transformation of data, as it moves through systems. Clear data lineage ensures transparency, accountability, and traceability, enabling organizations to track and validate the flow of information. To successfully build robust, scalable, and intelligent data systems, it is imperative to have a deep understanding of these data properties. By designing systems that can handle the complexities and dynamics of modern data, organizations can unlock actionable insights, improve decision-making, and maintain a competitive edge in today's fast-paced data landscape. Data volume is a defining characteristic of modern data environments, referring to the enormous and ever-increasing amount of data being generated, stored, and analyzed daily. From user interactions on websites and apps, to machine logs, sensor data, transaction records, and the outputs of AI models, the global data footprint is growing at an exponential rate, often doubling every few years. This shift means that data systems must now scale to accommodate not just gigabytes or terabytes, but petabytes of data, a scale that presents significant challenges in storage, processing, and querying. At these large scales, simply storing data is no longer sufficient. We need to ensure that data can be processed, queried, and retrieved efficiently and effectively. File formats such as Parquet, ORC, and Avro have become crucial as they support columnar storage, compression, and schema evolution. These formats enhance query performance and are optimized for large-scale analytics by reducing storage footprint and improving access times, which is essential when dealing with petabyte-sized data. Another vital aspect of managing data volume is implementing effective partitioning strategies. Partitioning allows us to organize data in a way that significantly improves query performance by reducing the amount of data that needs to be scanned. Without intelligent partitioning, queries on large datasets could take an unacceptably long time to return results. Additionally, tiered storage offers a cost-effective way to manage large volumes of data. Frequently accessed data, or hot data, is stored in high-performance storage, while older, less frequently queried data, or cold data, can be offloaded to cheaper, slower storage tiers. This strategy helps balance performance with cost efficiency. Underneath these strategies, several optimizations further enhance performance. Techniques such as column pruning, where only the necessary columns are read, predicate pushdown, which filters data earlier in the process, and bloom filters, which quickly assess whether data exists in a set, are critical for reducing scan times and improving performance when querying massive data sets. These optimizations enable data systems to handle large-scale operations with minimal latency, even as data volume increases. Managing data volume is not just about handling size, but about building intelligent, scalable systems that are designed to grow and evolve with the organization's data needs. We're no longer just concerned with how much data we're managing, but also how fast it's being generated, and more importantly, how quickly it needs to be processed and acted upon. This is the concept of velocity, and it's one of the most transformative shifts in modern data architecture. We now operate in a world where data comes in at a blistering pace, whether it's user behavior on websites, sensor readings from IoT devices, application logs, or mobile interactions. This data is constantly streaming in, often in milliseconds. More and more business use cases require data to be processed in real time or near real time. Think about fraud detection, personalized recommendations, operational dashboards, anomaly detection, or triggering alerts. These are scenarios where batch processing simply isn't fast enough. To meet these demands, we build streaming data pipelines that are designed for high throughput and low latency, often processing millions of events per second. But adopting real-time architectures requires a fundamentally different mindset. Instead of relying on monolithic batch jobs that process large chunks of data at scheduled intervals, we shift toward more event-driven systems, micro-batching, or even continuous processing, where data is transformed as it flows through the system in real time. This shift introduces a new set of engineering trade-offs that must be carefully managed. We need to find the right balance between latency, ensuring that data is processed quickly and timely, consistency, making sure the data remains accurate and reliable across multiple systems, and throughput, optimizing for the volume of data that can be processed at any given moment. This dynamic approach demands careful planning and architectural decisions to ensure that systems remain scalable, responsive, and performant. And with velocity comes operational complexity, message durability, and stateful processing, ensuring the system doesn't buckle under load or lose critical events. It forces us to think differently about time, responsiveness, and the flow of information, and pushes applications to operate at the speed of business. One of the most complex aspects of modern data is its variety, not just in the formats of data, but also in how and where it originates. Today's data pipelines are tasked with pulling information from an ever-growing number of heterogeneous sources, including APIs, server logs, application logs, real-time event streams, SaaS platforms, file drops, mobile devices, and IoT sensors. Each of these sources comes with its own set of quirks, delivery models, and unique data structures. This creates a multidimensional challenge where data isn't just different in format, e.g. JSON, XML, CSV, but also varies in structure, frequency, and context. These data structures themselves are highly diverse, typically grouped into three broad categories: structured, semi-structured, and unstructured. Structured data is highly organized, often in tables or rows, while semi-structured data, like JSON or XML, contains some organization but lacks a fixed schema. Unstructured data, such as images, audio, and video, doesn't follow any inherent structure at all. This variety not only adds complexity, but also introduces challenges in integration and analysis, which we've touched upon earlier in the presentation. One of the key difficulties in managing such data variety is handling schema evolution and variability. As new data sources are added and existing ones evolve, field names can change, data types may shift, and new attributes can appear unexpectedly. These changes can break pipelines and downstream consumers if not managed carefully. Building systems that can absorb these changes without disruption requires adaptability. This means using tools capable of ingesting, parsing, and transforming a wide range of data formats, often with real-time or near real-time responsiveness. Ultimately, the variety of data reflects the richness of the business landscape. Different teams, applications, and devices all contribute valuable pieces of information, each serving a unique role. But managing this diversity requires thoughtful architecture, solid engineering discipline, and a clear strategy to ensure that the resulting data pipelines are flexible, reliable, and scalable enough to meet evolving needs. Data engineering is the discipline that underpins all data-related activities in an organization. It is responsible for building and maintaining the foundational systems that enable organizations to collect, store, process, and serve data at scale. In many ways, data engineering acts as the backbone of any data-driven organization, ensuring that high-quality, reliable, and timely data is available for critical business functions like analysis, reporting, and machine learning. Without the right data infrastructure, organizations would be unable to make data-informed decisions, which can ultimately lead to missed opportunities and inefficiencies. What truly sets data engineering apart is its core focus on scalability, maintainability, and security. It's not just about writing ad hoc ETL scripts. It's about designing and architecting end-to-end data pipelines that ensure raw, unrefined data is transformed into structured, usable formats. These formats are optimized for analysis, decision-making, and driving business value. Essentially, data engineers create the pathways that ensure data flows smoothly from source to destination, enabling other teams to derive meaningful insights from it. In many ways, data engineers are akin to the plumbers of the data world. They design and maintain the pipelines through which data flows, moving it from where it's generated, whether it's from APIs, databases, files, or streams, all the way through to the end consumers. These consumers might be business analysts, data scientists, executives, or even automated systems that rely on real-time data for decision-making. The pipeline ensures that the data is clean, accurate, and ready for consumption. As organizations continue to integrate more advanced technologies such as AI, real-time analytics, and automation, the role of data engineering has only grown more critical. You can't have intelligent systems or perform advanced analytics without a robust data foundation. The ability to capture and transform data quickly and efficiently is what allows businesses to stay competitive in today's data-driven world. Data engineers are not just building systems. They are creating the infrastructure that powers the intelligence behind business operations, enabling smarter decisions across every level of the organization. To understand the role of data engineering, it's helpful to look at the modern data lifecycle, a high-level view of how data flows through an organization. The lifecycle typically moves through five core stages: ingest, store, process, serve, and observe. It starts with ingest, where data is captured from diverse sources like APIs, logs, databases, and IoT devices. Then store, organizing raw, staging, and curated data in lakes or warehouses for accessibility and governance. In the process stage, data is transformed, enriched, and validated through batch or real-time pipelines. Serve makes this data available to users and systems via dashboards, analytics tools, ML models, or applications. Finally, observe, monitoring pipelines, tracking lineage, and ensuring data quality to maintain trust and reliability. Data engineers are involved at every single stage of this process. Throughout all these stages, the data engineer's goal is to enable automation, scalability, and cost efficiency, ensuring that the data ecosystem can grow and adapt as business needs evolve. It's important to note that the data lifecycle isn't always a one-way, linear pipeline. In modern architectures, especially with real-time systems, feedback loops are common. Data from the serve stage may trigger immediate actions or updates that flow right back into ingestion and processing. This creates continuous, event-driven data flows that demand low latency, highly responsive engineering. This is an illustration of the life cycle where each layer plays a vital role in creating a scalable and intelligent data ecosystem. It all begins with ingest, connecting to a diverse array of data sources, from APIs and relational databases to event streams, mobile apps, IoT devices, and logs. These sources emit data in different formats and frequencies, and ingestion pipelines must be resilient, scalable, and capable of handling both batch and real-time flows. Next is store. Once ingested, data lands in structured layers within data lakes and warehouses, typically organized into raw, staging, and curated zones. These layers help manage data quality, schema evolution, and access control, while supporting both historical and real-time analytics. Then comes process, and this is where raw data is transformed, validated, and enriched to make it useful. Whether through batch jobs or real-time streaming frameworks, processing involves applying business logic, standardizing formats, and preparing data for consumption downstream. With data ready, we move to serve, exposing curated datasets through analytics tools, dashboards, machine learning pipelines, or APIs. This is where business users, data scientists, and applications access the insights they need efficiently and securely. Finally, observe, where monitoring and observability are essential to ensure trust and reliability in the system. This includes tracking pipeline health, capturing lineage, auditing changes, and continuously validating data quality to catch anomalies early and maintain compliance. Together, these layers form the backbone of scalable, resilient, and intelligent data ecosystems. Operational systems, OLTP, are systems that are specifically designed to handle high-volume, real-time transactional workloads. These systems are essential for processing real-time business transactions and support the daily operations of an organization. OLTP systems focus on ensuring high availability and low latency so that transactions can be processed quickly and reliably. A key characteristic of OLTP systems is their use of normalized schemas, which help to reduce data redundancy and ensure data integrity. This design allows for efficient storage and retrieval of transactional data, making it easier to handle frequent updates, inserts, and deletes. By eliminating data duplication and organizing data into smaller related tables, normalized schemas streamline the process of maintaining consistent, accurate records. As a result, OLTP systems are well suited for applications requiring real-time transaction processing, such as order management, banking, and inventory systems. This approach ensures that any changes made to the data are immediately reflected across the system, providing up-to-date information at all times. OLTP systems are widely used in applications like order processing, inventory management, and customer relationship management. Examples of OLTP systems include relational databases such as PostgreSQL and MySQL, as well as NoSQL stores like MongoDB and DynamoDB, which are designed to handle high throughput and low latency transactions in more flexible, schemaless environments. These systems form the core infrastructure of modern business operations, supporting critical processes that rely on fast and accurate data. Analytical systems, OLAP, are specialized systems built to handle complex queries and perform aggregations over large datasets, making them ideal for business intelligence (BI) and decision support systems (DSS). These systems are specifically designed to facilitate querying and reporting on massive volumes of data, providing insights that support strategic decision-making. OLAP systems prioritize throughput, allowing for the efficient execution of large-scale queries, and focus on denormalization to optimize performance. By simplifying the data structure, denormalized databases reduce the need for complex joins, enabling faster query execution. This design is particularly beneficial for analytical workloads where speed and efficiency are paramount. Additionally, OLAP systems are optimized for aggregations, which are essential for summarizing data and identifying patterns across extensive datasets. The denormalized structure allows for faster access to aggregated values, making OLAP systems ideal for business intelligence (BI) applications, data analysis, and reporting, where users need to quickly derive insights from large volumes of data. Examples of OLAP systems include popular data warehouses like Snowflake, Redshift, and BigQuery, all of which support high-performance querying and are built to scale with the demands of modern data analysis. These systems are the backbone of analytics workflows, enabling businesses to gain actionable insights from their data and make informed, data-driven decisions. Big data architectures are intentionally designed with layered data zones, each serving a specific purpose in the data lifecycle, from raw, unprocessed ingestion to highly curated, analytics-ready datasets. This layering allows organizations to progressively refine, validate, and optimize data as it moves closer to the point of consumption, ensuring better control over data quality, lineage, and usability. One key architectural distinction lies in schema management. Data warehouses typically enforce schema on write, validating and structuring data before it's stored, while data lakes favor schema on read, providing more flexibility by applying structure only when the data is queried. This difference shapes how systems handle data reliability, adaptability, and governance. Another cornerstone is the decoupling of storage and compute, which modern architectures leverage to scale each component independently. This separation enables cost optimization and resource elasticity. Compute can scale up for heavy workloads and scale down when idle, while data remains durably stored and accessible. The data transformation strategy also defines architecture. Traditional ETL models focus on upfront transformation before loading data, while ELT pushes raw data into the system and transforms it within powerful, cloud-native warehouses. This shift supports faster ingestion, more agile modeling, and greater use of shared compute resources. For these systems to work at scale, metadata management and governance tooling are essential. They ensure data is discoverable, trustworthy, and compliant, enabling secure access, lineage tracking, and consistent definitions across teams and tools. We're witnessing a growing convergence between architectural models blending the best of both worlds, the structure and performance of warehouses with the flexibility and scalability of lakes. A data warehouse is a purpose-built platform designed specifically to store structured, curated, and historical data for analytical purposes. It acts as the central hub where clean, governed data is consolidated to support data-driven decision-making across an organization. Modern data warehouses are optimized for performance using technologies like columnar storage, materialized views, and intelligent caching. These techniques significantly improve the efficiency of analytical queries, particularly those involving large aggregations, complex joins, and multidimensional filtering, which are common in business analysis. They're engineered to serve business intelligence workloads, powering dashboards, reports, and ad hoc queries. Because these tools demand reliable, consistent data, the warehouse follows a schema on write paradigm, where the data is modeled, cleaned, and validated before it's stored. This ensures strong data quality and integrity at the point of entry. Warehouses typically ingest data from operational systems, often through ETL or ELT pipelines. Once inside, this data is used to support read-heavy analytical workloads that follow well-defined access and usage patterns. One of the key value propositions of a warehouse is its ability to serve as a single source of truth, providing consistent definitions for metrics and KPIs that are used across departments. This promotes trust in the data and alignment in reporting. In recent years, cloud-native data warehouses have become dominant. These platforms offer serverless architecture, elastic compute, and the separation of storage and compute resources, which allows organizations to scale efficiently based on demand without upfront infrastructure investment. A data lake is designed to store raw, unprocessed data exactly as it arrives, whether it's structured tables, semi-structured JSON, or completely unstructured content like images, videos, or PDFs. It serves as a central repository where data is retained in its native format without any transformation applied up front. This architecture allows for great flexibility, supporting all data types and enabling what's known as schema on read. That means the structure and interpretation of data are deferred until the time of analysis, making data lakes highly adaptable to a variety of downstream use cases. Data lakes can ingest from virtually any source, logs, IoT devices, applications, or third-party APIs in both real-time and batch modes. This makes them a popular choice for environments where data velocity and variety are high. Because storage is typically low cost and decoupled from compute, data lakes offer unmatched scalability. They're often implemented on cloud object storage platforms like Amazon S3, Azure Data Lake Storage, or Google Cloud Storage, which allow organizations to store petabytes of data economically. Data lakes shine in areas like data science, machine learning, and exploratory analysis, where raw access to large volumes of diverse data is essential. However, with this flexibility comes a trade-off. Governance is minimal by default. There is no built-in enforcement of data quality, schema validation, or consistency, which means these must be managed through external tools and practices. Without proper cataloging, metadata management, and oversight, a data lake can quickly deteriorate into what's often called a data swamp, a vast, unusable pool of disconnected and untrusted data. A data lake house is a modern hybrid architecture that brings together the strengths of both data lakes and data warehouses. It aims to combine the scalability and flexibility of a data lake with the governance, reliability, and performance of a data warehouse. Like a data lake, it can store raw data in its native format, accommodating structured, semi-structured, and unstructured data. However, unlike traditional lakes, lakehouses also support schema enforcement and transactional guarantees, providing the structure needed for analytical workloads. One of the defining capabilities of a lakehouse is the ability to perform analytics directly on lake storage without the need to copy data into a warehouse. This is achieved through performance optimizations such as indexing, caching, and query acceleration layers, enabling fast, SQL-based access to large-scale datasets. With this architecture, organizations can now support business intelligence, reporting, and machine learning workflows on the same platform, reducing duplication and accelerating time to insight. Data lake houses are typically built on open columnar file formats like Parquet or ORC, layered with advanced table formats such as Delta Lake or Apache Iceberg. These formats enable transactional integrity, efficient metadata management, and schema evolution directly on top of object storage. A key benefit is that lakehouses eliminate the need for complex data movement between data lakes and warehouses, which historically created delays, data silos, and additional infrastructure cost. They also support both streaming and batch processing on unified datasets, simplifying the pipeline architecture and enabling real-time analytics alongside historical analysis. Advanced features like data governance, time travel, versioning, and rollback are now part of the lakehouse paradigm, helping teams manage data lineage and correctness more effectively. Ultimately, the data lakehouse helps reduce cost and complexity by converging storage and compute on lake-native infrastructure, offering a single, unified platform for both exploratory and production-grade analytics. Data mesh is not just a technology but a socio-technical approach to data architecture that emphasizes decentralization, both in how data is owned and how it's managed across an organization. It represents a significant shift from the traditional model of building large centralized data platforms. Instead of funneling all data through a central data team, data mesh advocates for domain-oriented ownership, where individual business or product domains are responsible for the life cycle of their own data, from creation to maintenance and quality assurance. In this model, each domain team treats their data as a product, complete with clear service level agreements, SLAs, for availability, quality, and discoverability. This mindset fosters accountability and ensures that data is trustworthy and usable across the enterprise. Data mesh promotes the use of self-serve infrastructure, tooling, and platforms that empower domain teams to autonomously build, deploy, and operate their data products without relying heavily on a central data team. To maintain coherence and consistency across domains, federated governance is introduced. This allows for compliance, security, and standardization without reverting to centralized bottlenecks, enabling a balance between autonomy and control. The model also encourages collaboration between data producers and consumers, ensuring that the data being published meets the needs of downstream users and promotes interoperability across the organization. Data mesh is especially well suited to large, complex organizations with many independent teams and diverse data requirements, where a centralized architecture can quickly become a constraint. However, it's important to recognize that data mesh is as much about organizational culture and operating model as it is about technology. It requires a mature DevOps culture, strong platform engineering, and a shift in mindset around data ownership and accountability. Finally, data mesh is not intended to replace technologies like data lakes or lakehouses. Instead, it complements them, providing a decentralized, scalable framework for managing and delivering data using whatever storage and processing technologies best fit the use case. Thank you for joining us in this video. If you haven't already, we'd love for you to subscribe to our channel to stay updated with our latest content. We look forward to sharing more insights with you in another video. Until then, keep exploring. And thank you for watching.